is kind of a first for me because I have only met John and Vicky virtually. And usually with the Know Your Islanders, I have actually met them in person and gotten to know them a little bit, but this is the best means to do it during COVID. So they actually several months ago, pre-COVID, came into the library and introduced themselves as island residents to my colleague Leslie Baker, and they actually offered to share their expertise with us, and we jumped on it, and so that's why we're here now. So I want to just go ahead and turn it over to you guys and let yourselves introduce yourselves, because as I said, I don't know that much about you. So Vicky and John, take it away, please.
Okay, so I can introduce Vicky, who's got a PhD in atmospheric physics from the University of Leeds in the United Kingdom. She worked at a variety of different jobs prior to that, as a baker, as a bookseller. I don't believe she was ever a candlestick maker, but a British Antarctic Survey graduate student project got her through the PhD, and then she worked at the University of Auckland in New Zealand and Toronto in Canada. Her work with the Canadian Space Agency is of international repute as a senior program scientist for planetary exploration. Currently a casual employee, but previously a dedicated public servant who is well known to NASA as someone who could bring good instruments to their missions with an outstanding science team and team leader. In particular for the NASA Mars Phoenix lander mission, which landed on Mars in 2008, spent the summer operating from University of Arizona. NASA ordered Vicky the Exceptional Public Service Medal for her great work as a science lead on that mission. And she also added things to the Curiosity rover mission, the Mars Science Laboratory, and the ESA ExoMars Trace Gas Orbiter mission. So I'm happy to be here with her.
And I first met John in 2005 in his second stint at NASA headquarters when he was Planetary Protection Officer and I was the Canadian representative to his very well-run and interesting advisory committee. So planetary protection itself, you'll hear more about, but it's really an amazing policy that was put in place way back at the beginning of the space age that protects other planets from potential contamination from Earth. So a lot of foresight, and John has been very instrumental in keeping that policy up to date and engaging in many experts and different bodies across the States. He's also been NASA's senior scientist for astrobiology, and then has left NASA on a couple of occasions and has worked in ocean relevant work at the Woods Hole Marine Biological Lab, so the East Coast version, I guess, of Friday Harbor Labs, and at East Carolina University as their director for the Institute for Coastal Science and Policy. So he's also still active, now working under our business as Friday Harbor Partners.
So I've resigned from the federal government 3 times. I hope to do it again sometime too. So we're here to talk to you about life, past, present, and future. And we'll dwell mostly on the activities of the present as they address the past and the future, and hope that that is of some interest to you. And thank you all for coming. I really appreciate that. Next slide.
So this is an amazing picture from the surface of Mars. This is from 2014, taken by the Curiosity rover. And that tiny, tiny speck there is Earth. And it's just amazing how insignificant we are, even from one of our nearest neighbors in the solar system. And we're here to talk about the search for life, particularly focused on Mars. But it's really amazing that that we are all on Earth right now having this Zoom, and even from the surface of Mars there would be no evidence of this kinds of activity. So Dr. Rummel, tell us.
We laugh at this one because while there's much evidence that's coming out about what happened when, we really don't know what lit the candle, what lit the spark in the first place. Between the formation of the Earth, its core, and the formation of the moon, something slightly thereafter, around 4 billion years ago, we see evidence of ample biological material life on Earth. And we really don't know how that happened, whether or not it was material that was here in the beginning or whether it's material that was brought in after the Earth started to cool down and have lots of water on its surface, etc. We do know, however, that as time went on, life interacted with each other, and my colleague Lynn Margulis would tell you that there was ample symbiosis, and eventually that happened. But the scientific establishment right now, when you ask them, how did life start? You get the same answer that Tristan would give at age 7, not a clue. Go ahead, Vicky.
So this is a map of Earth. And what we see here is that the little gray patches are the only places where you can still find rock that is more than 2.5 billion years old. So that kind of gap in our understanding of how life might have emerged on Earth. Most of the geological record and fossil evidence has been destroyed because Earth is such a dynamic planet. But rocks of 2.5 billion years old are all over Mars, especially in the southern hemisphere. So they are, Mars is a very good place to start with that whole idea about life and the origin of life.
Yeah, the clues to the origin of life are definitely potentially available in the highlands of Mars. And Mars, because of certain astronomical observations, et cetera, for a long time has been of interest to people who are interested in life off of the Earth. And whether it's Percival Lowell here in the upper left corner, H.G. Wells there on the right, Werner von Braun, Carl Sagan, Kim Stanley Robinson, Penny Boston, Sally Ride, or even that woman in the lower right, Vicky Hipkin, Mars remains to be of great interest. Next slide.
So this is pretty remarkable because this is an actual New York Times article from 1911. And this was the report from Percival Lowell, where his interpretation of what he was seeing through the world's most powerful telescope at that time was that Martians were building canals. And this is because he saw that some lines that he observed, and it was hand-drawn at that time, the maps, it looked like they were changing over a period of time, and he interpreted it as a civilization of Martians who were active, and we knew no better at that time. Then come 1996, we've had some so-so movies, and at this time, I think that there's common understanding that we don't have a vast civilization of Martians alive today. But as recently as 1938, with the very famous radio broadcast of War of the Worlds, enough people listening into there really did believe for a short time that the Earth was under attack. And so our scientific knowledge of Mars has really come about quite recently. And really starting with the space age.
Yeah, this is an image from what's the Mariner 4 mission that went to Mars in 1965. And it didn't have a great imaging system, but it was a long way away for that time and place. And Mars was a major disappointment because what they saw were craters just like on the moon. And as a result, there was a widespread concern that Mars wasn't going to be the kind of Mars that it was for Percival Lowell or even Schiaparelli, with lines drawn and canals under construction, et cetera. This was the first major evidence against that. And it caused some consternation in the scientific community, which was only improved later with better spacecraft. What you have on the left is the Viking mission to Mars. There were 2 of those sent in 1975, landed in 1976. In the pod on top of that is the Viking lander mission. Everything inside of that pot has been baked in an oven at a temperature of 111.7 degrees Celsius for over 50 hours, so that we didn't take any live Earth organisms to Mars and to try to culture them. The lower part was what we would call the cruise stage now, but also turned into an orbiter once the lander was dropped off. On the right, Mariner 9, where you have ample evidence for liquid water flowing on the surface of Mars for long periods of time. And so in 1971, 75, things started to look better for Mars in terms of the potential for life. But there was some concern because at that time, they didn't detect any organic material in the soil of Mars.
Q 1996. And here we have the Allen Hills meteorite. So this is a meteorite that was identified as being from Mars by comparing the gases that were captured in little bubbles inside the rock with what the Viking missions had measured on Mars. So we knew it was absolutely from Mars. It was discovered in 1984, but in 1996, a peer-reviewed scientific paper was published reporting that there were several different lines of evidence that suggested that there might have been microbes active in the early part of Mars history. So you see a high resolution electron microscope image here of some strange structures in the rock. That was just one line of evidence that said that there might have been some life activity, very primitive life activity on Mars. The rock was dated to be 3.6 billion years old.
4 billion years old, yeah.
Yeah, and so a lot is known about that because of the ability to apply the very most sensitive Earth lab instruments to rocks. And as you'll hear, it's still a desire to bring rocks back directly from Mars to do some of that analysis on Earth.
Go ahead. And of course, what 1996 engendered was the follow-up of Follow the Water, where missions were launched specifically with the consideration that we might be able to detect water on Mars or places where water had flown in the past and could have then hosted life. So the Mars Global Surveyor, Mars Polar Lander, we had Mars Pathfinder, both between MGS and MPF, as we call them. Though they were launched in 1996, landed or orbited in 1997. And that was quite an interesting time because we were just learning new systems about how to land safely on Mars. The Mars Observer spacecraft had been lost around Mars in 1993. Odyssey launched in 2001 and had very capable instruments on it, able to detect hydrogen and related materials in a very interesting way that showed that there was probably large amounts of ice under the Earth.
So what we see here is a progression from SEEK, which were the orbiter missions that were trying to image the planet from the surface with new capabilities to look for ice and things. And then In Situ, which were the lander and the rover missions. And what we're heading towards is the sampling, the idea of sampling the surface and being able to bring things home. So at this stage, NASA has been the leader in getting to Mars. We don't show here some earlier attempts by the Soviet Union. We have the European Space Agency has been successful in bringing missions to Mars, and India as well back in 2013. But only NASA to date has managed to land successfully on the surface of Mars. And the four themes there are still current and are motivating all of the Mars missions that are being planned internationally. So what do we know about Mars today? So this is kind of a summary chart. The images are to scale of the Earth and Mars. You can see there's white on both images. So, yes, Mars has an ice polar cap, and it also has cloud, water ice cloud like Earth. So it does have an atmosphere. but the atmosphere is much thinner than Earth. It's about 1%. And that means that water would actually evaporate from the surface if it was to be introduced onto the surface at Mars today. And that's a major interest because what that suggests is that there's been some major climate change on Mars over its history. The other thing you see here is that by chance, really, both Earth and Mars have a day that's a similar length. So you get 40 minutes more sleep if you were on the surface of Mars than on Earth. And that's something we did enjoy when we were working the Mars mission here back on Earth at University of Arizona, where we lived on Mars time for the duration of our mission. We were commanding from University of Arizona every morning so that as our solar-powered spacecraft woke up, our commands would be transmitted to its memory at the start of its day. Oops. So here's the Phoenix mission. It was a landed mission to the northern hemisphere, to an area of permafrost, and it was really sent there to confirm that water ice on the surface of Mars. And the mission you see in the top left there, a little lander, it was only about 1 meter diameter and a meter for each of the solar panels that you see on each side. It had a digging arm, and the image immediately beneath it is the trench that we dug. It was a very complicated thing to do robotically, semi-autonomously, to dig. And then this white material, some of it is ice, and some of it turned out to be some interesting salts as well. But we were able eventually to scoop it up, put it in a little oven, and put the sample into a spectrometer, and say definitively that we have water ice on Mars. The other thing that we have on the bottom right here is an image from a Canadian experiment. So Canada contributed the weather station to this mission. And here we had a LiDAR, which sends beams of light upwards that bounced off a layer of cloud. And again, we were able to say this is water ice cloud, and the fall streaks you see were evidence of snow on Mars. So this mission really told us more about the polar regions of Mars and snow and ice. And the top right-hand picture here is another amazing feat of technology. So that the tiny little image you see there against the crater was the Phoenix mission captured mid-descent. The little lander was underneath a parachute, and it was captured by a camera on a separate orbiting mission. And that all had to be done autonomously. It had to point without anyone on Earth being able to point it. Back on Earth, we had to predict where it was going to be and set up a command so the orbiter would look in the right direction at the right time. And it was able to pick out something that was only a few meters across in the Mars atmosphere. So really quite amazing, the kinds of technologies and the ingenuity that Mars inspires.
Shift change. What were you going to say about this one?
So here we have Curiosity, and this was another stream of evidence to say that there'd been water on the surface of Mars. So this is a NASA rover mission that's still active on Mars. It landed in Gale Crater, where it looked as if there had been some evidence of water features in the landscape as well in the past. And indeed, that's what they found. They found things that look remarkably like lake bed sediments on Earth. And we could drill into those and put samples into various instruments. It's called the Mars Sample Science Laboratory because there were quite sophisticated instruments to detect organics that had been miniaturized to put in the back of this rover. And then the bottom right-hand corner, you have a picture of a stream bed on Mars, a slightly reddish one, compared to a stream bed on Earth. And we saw rounded kind of rocks that showed pebbles that had been worn down by water. And there was a strong scientific consensus that we were looking at ancient stream beds on Mars. So these two missions have gone down to the surface to confirm some of these earlier ideas about water on the surface. And where we are today is that they think that the surface of Mars, here we're looking at an image of Mars as imagined and modeled through climate models for the planet, saying that about 3.5 billion years ago, there had been an ocean on the surface of Mars. And today we have a Mars Global Surveyor composite image from 2001, about that kind of time frame, which shows our dry, familiar red planet. And so it remains a big mystery. What exactly was the event or the process that changed Mars from a very Earth-like planet to the dry planet today? Another mystery that has arisen more recently is the finding of trace amounts of a gas in the atmosphere of Mars by both initially by one of these orbiter missions and then also on Curiosity, that very occasionally they can measure a pulse of methane, not very much. But on Earth, most of the methane in the atmosphere comes from microbes. It's created by microbes. And with the presence of oxygen, they're one of the strongest signal our planet has as a disk that the Earth is alive, because those two gases will destroy each other. They'll chemically react unless they're continuously being produced. So the whiff of methane on Mars got people excited again about the possibility of a subsurface environment where there may be some microbes that are still active on Mars. There is another source of methane on Earth. There's a process with rocks and water, a type of serpentine rocks that are associated with the seabed. They can react and they can also produce methane. So there are non-biological ways of creating methane, but at this point, the subsurface remains quite a mystery on Mars. There's been no mission able to really penetrate down any further than a meter or so. And we have remote sensing techniques are being employed in upcoming missions to try and look further below the surface. There have been some radar on with very coarse resolution able to see a few kilometers down, but only in chunks of 500 meters at a time, and they haven't found any. They haven't found very many places where they think there may be liquid water today. They're beginning to get some new results from the radar measurements that deserve more follow-up, that to suggest there may be some areas of liquid water in some places and some seasons. So 2020 is a big year for Mars exploration. So we came to the library to suggest this talk, knowing that very unusually, there were actually 4 planned missions that were going to be launched this month. One of them has now been delayed. The European ExoMars lander rover mission was going to launch this year, and it has officially been delayed because of COVID. It was being put together in the north of Italy, and now will likely launch in 2022. But what we're going to talk about now is the Emirates Mars mission HOPE, a Chinese Mars mission, Taiwan 1, and NASA's follow-on to Curiosity rover, the Mars 2020 rover mission Perseverance. The HOPE mission was due to launch today, has been delayed once till July 17th, and we heard today that they still have bad weather, so they're looking at a future delay. So what you saw in the earlier chart of missions were the successes. There have been a lot more failures. It's a 50% success rate now in getting to Mars. It's getting better as time goes on, as there's more experience and more technology. But here we have the potential landing sites of the Perseverance rover and Tianwen 1. So they're both landing, potentially landing in this change in topography from this very ancient southern area to the flat, smoother area that's associated with these ancient oceans. So everyone's interested in going to the intersection of old terrain and water. I think these charts will be available later to read. I'm not expecting people to read the small text there. So how do we get to Mars? Well, we can start at Webb Street, and there's a signpost, Mars, 54 million miles away. And you can pick up your boarding pass. So the NASA program allows you to go online and register yourself, and you will get a boarding pass to go to Mars. It's too late for Mars 2020 mission, but they're already taking reservations for their future Mars missions. So why 2020 for 4 missions? Well, it's to do with planetary alignment. And this is a chart that shows that every 2 years, Earth, the little blue round spheres, and Mars, the little reddy colored ones, align so that they are close to each other in orbit. The Mars orbit is twice as long as Earth's. It takes almost 2 years to go around the sun. And so there are times in the year that Mars and Earth are actually very far away from each other, opposite sides of the sun. But energetically, for fuel and the duration of the journey to Mars, it's much more advantageous to launch when the 2 planets are close to each other. So 2018 was the closest approach for a long time, and so we saw some missions launch there, and 2020 is the next best opportunity for quite a long time. So we're seeing 4 missions try and launch, and they have really this month till the end of August, where the planets start to drift away from each other again, and it becomes a lot more difficult to get there. The other comment is that because of that great distance, it actually takes time for commands to reach Mars at all. It takes between 3 minutes and about 20 minutes just for a signal to go from Earth to Mars. And so what you have back on Earth is you have a room full of engineers that are controlling the position of the spacecraft, and in the end, the rover. And then a room full of scientists who are planning the sequence of measurements to make every day. And the data arrives typically from a rover mission. They'll send it up to one of the orbiters. They'll only do that maybe twice a day. And then the orbiter will send it back to Earth, and all of those images come back down, and the science team will look at them and see which experiments from the day before were successful and what new ones to plan. So this semi-autonomous planning for Mars is real. There's not any way of using a joystick and actually getting something to move on Mars. It's just too far away all the time. So come to the first mission now. This is the Emirates Mars mission, the Hope mission. And this is a very interesting story. So back in 2014, I think it was, the United Arab Emirates founded their space agency. And they announced to the world that they were planning a Mars mission. They had very clear ideas about why they wanted to do this. This is going to be the first Arab Mars mission. And where they were is they could see that the country had a technology sector that was very much geared to oil production, very single product orientated. They had good engineers, good technologists. They did not have as strong a science section, a science culture. they had rather few numbers of researchers, and they had an increasing population of youth. It was predicted that there would be something like 100 million Arab youth in the next decades. And what they wanted through this Mars mission was to both inspire that generation to think of a vision that was, you know, more than oil and more than conflict, a vision where they could have jobs and ambition and training and restart the whole further development of science and research in the universities. And they basically came to the international community and said, you know, we're going to do this. You know, we've got a budget for it. We're really excited about this. This comes from the heart. We really want this to happen for the youth of tomorrow. And we're looking for international partners. We'll be very happy to work in partnership with you to fly this mission to Mars. And so NASA and particularly the University of Colorado stepped up to partner with the Emirates, and they have built this mission together. So there've been about 150 Emirates scientists and engineers, and a similar number of US scientists and engineers working to build this spacecraft. And it was built at University of Colorado because one of the scientists there had just completed the first year of science operations for his mission MAVEN, which was looking at the escape rate of the atmosphere from Mars as one of the hypotheses to understand why climate might have changed. So this is the spacecraft they built. It's quite a small orbiter, but this is a fantastic, amazing first for the Arab world. And the science that they were doing is complementing the MAVEN mission. So here you see the image of planet Mars. They have 3 instruments, and they're going to look at water vapor and dust storms in the lower part of the atmosphere, and look at how water then reaches the upper part of the atmosphere and escapes into, is essentially peeled off by the solar wind and is lost from the planet. And so they have instruments that can look at all these different layers, and putting it together in that way is why they're calling it the first complete picture of the Martian atmosphere. There have been lots of other atmospheric experiments, but they're really going after complementing MAVEN to look at this atmospheric escape problem. And so, you know, going back to this idea about climate change and how much of the loss of water you can explain just by Mars' lower gravity. So here are the 3 instruments. These are very typical instruments. So infrared can tell you about water vapor and dust in the lower atmosphere. The photographs can tell you about the cloud systems. And ultraviolet is the kind of measurement that you use to look at the particles that are escaping from the top of the atmosphere. So the next mission to launch is planned anyway as the China National Space Agency mission Tianwen-1. And there's little information that is being publicized about this mission at this time. And this is very similar to when China sent its first missions up to the moon a few years ago, that the culture is much more concerned about failure. And so they don't want to generate a lot of publicity and attention until the mission has succeeded. And we'll hear a lot more about Tianwen, I imagine, once they've had a successful launch and then the other stages in their mission. What we know about it is that they're really being extremely ambitious. For their very first mission to Mars, they are planning an orbiter, and with I think 6 instruments on board, a radar to look at subsurface ice, a magnetometer to look at the magnetic field around Mars, to look at atmospheric escape again. And then they have a rover. And this is an image that has been released, and the rover looks remarkably similar to the earlier Mars exploration rovers developed by NASA. You can see some of the same design elements in the wheels and things. So this is going to be carrying, I think, 5 instruments, and it will go to, as we said earlier, one of these outflow areas where they're looking that there might have been evidence of water in the past. They are looking to land in a much flatter area than Mars 2020. And that'll be because going to the more interesting, perhaps, parts of Mars with some more detailed river valleys and things is a much more difficult landing proposition. So we look forward to hearing more about the Chinese mission as it's launched.
Okay. So the next US mission that happened is called Mars 2020, and it's known as Perseverance in the rover phase. What has landed is actually a rover from on a bridle that comes all the way from hovering spacecraft. The 4 goals that where Mars 2020 is supposed to contribute is the science goal, determine whether life ever arose on Mars, characterize the climate of Mars, characterize the geology of Mars, and prepare for human exploration. And all those things go together as part of a package. The landing site for Mars 2020 Perseverance rover is called Jezero Crater. Jezero Crater is an ancient river bed. And this was something that was formed over a period of perhaps 400,000 years and more. And it may have actually been covered up with other layers of Mars for a while. But this is the kind of a structure that makes sedimentologists very happy, because they think that organics could have been trapped and that they can find perhaps even microbial life remnant from an earlier era of Mars when it was warmer and wetter. This is a cool spacecraft that you have. It's about the size of a Mini Cooper. And of course, what they have is a subsurface radar looking for ice rim facts from the Norway Defense Agency. Mastcam, Supercam, MEDA is a weather station from France. I'm sorry, from Spain. And MOXIE is a device that's supposed to go ahead and split CO2 into carbon monoxide and oxygen. And we'll see how that works. It's a very interesting process. It's totally unlike what we do on Earth, where to get oxygen from green plants, we go ahead and split water. But we'll see how well that can do. That's from Massachusetts Institute of Technology. And this is a spacecraft of extraordinary capability that's powered by a radioisotope thermoelectric generator. The decay of plutonium puts together enough heat to go ahead and run the spacecraft throughout its entire lifetime. And that lifetime may be considerably long. Right now we're on the 7th year or so of almost the 8th year of the Curiosity spacecraft. But we'll see how they do. They're also taking along a little notional helicopter, which will be a very comforting ride because it's got to go at 2,400 RPM. But that will be a future pathfinder for missions in the future, we hope. And of course, now that once you get on board and you take your boarding pass chips with you, we have a permanent intellectual beachhead on Mars, if nothing else. We also want to make sure it's very, very clean. Mars 2020 will be the first spacecraft that we're using to actually grab samples that we can bring back to from Mars to Earth on a sufficiently capable spacecraft that can take that from the Martian surface, launch it into Mars orbit, have that orbiter picked up and packaged appropriately for Earth safety, and then it will land on the Earth sometime around 2031 if things go as currently provisioned. But we're not sure exactly how it goes. They have an extraordinary challenge in getting rid of most, if not all, Earth microbes and organics. So NASA does a tidy business in keeping organisms off of other planets and places where they can grow and thrive, and in making sure that we don't bring back something that might harm the Earth's biosphere. A variety of things you can find looking at the NASA website under planetary protection. I won't go into that too much. Launch is supposed to be no earlier than the 30th of July. They had a couple of hiccups in ground handling. And the cruise and approach 7 months later. The tight part of the mission is entry, descent, and landing, which takes about 7 minutes for the system. And then surface operations will continue. And we hope to get samples back in 2031 or thereafter. Entry, descent, and landing can be visualized pretty easily if you look at what happened to the spacecraft for Curiosity. This is the peak stage. Things finally get to Mars. And then the spacecraft goes in. It's got a heat shield. It just dropped off a couple of tungsten weights. It's got a back shell. And inside of that is the entire Curiosity rover and all the instruments. And it goes through the atmosphere of Mars. It's very hot, very difficult. Mars is one of those places where it's almost worse than it has an atmosphere. This slows it down by about 10 times from the 12,000 miles per hour approach speed. When you go to Mars, you leave Mars and then come back to it. So Mars is overtaking the spacecraft very quickly. When you launch the world's largest supersonic parachute, and then drop the heat shield and continue your descent. And as the descent goes forward, you're looking to make sure that you're landing in the right place. You drop the descent stage, which is very similar to the descent stage of Viking, only instead of Viking having everything on top, this has your rover on the bottom. It's going to drop the rover down on a particular bridle, as we call it. And that'll happen momentarily. A lot of Mars material is whooshed up by those jets, but mostly in a different direction. We get to the landing, bridle comes down, wheels pop out. This is a very complex system. It probably takes you about 141 or more pyros, things that explode and make different things happen. There goes the landing stage, and we now have a happy rover, if not a happy little girl, on the surface of Mars. So in Mars 2020, the rover's new landing techniques allows it to get much closer to the center of where it wants to go than previous spacecraft. It'll have a comparison of descent photos from orbital images and divert if necessary if they find themselves on the wrong path. So that's an adaptive navigation, very nice system. This is, as I said, the beginning of a Mars sample return campaign mission. Land in Jezero crater, pick up great samples, pop them into your little chest of samples that the spacecraft carries with it, and then make its way to someplace where the sample retrieval lander can land, pack it full of samples, and then the Earth return happens with a rendezvous of the orbiting sample container with the European return orbiter, which will then bring things back to the Earth in a containment facility that would be the marvel of any disease lab on the Earth. So this is what we would call in the business a bat chart kind of a thing, where you have the the different kinds and parts and pieces of a Mars sample return. But effectively, it's a very complex undertaking that needs to happen everything on time with very few slack spots if you're going to get your sample back safely to the Earth. This is something that we've been lucky to have this collaboration with the Canadian Space Agency, because one of the things that this Mars sample return mission needs is a capability for a rover to grab the samples and package them into a transportable activity to launch on the Mars Ascent vehicle later on. Vicky?
Yeah, so this was a technology demonstration that Canada did to show to NASA and the European Space Agency as part of stimulus money that the engineering sector had got in Canada. And we actually had to go and do this experiment down in Huntsville in Utah, because though Canada has many dry deserts, we couldn't get the appropriate weather to plan a campaign up in the Arctic deserts. And it was a great pleasure to be in Huntsville for a short time. This is Mars on Earth. And I think we worked with NASA. They were very happy to see the demonstration of this fetch rover element. And Canada is talking to the European Space Agency about being involved in the design of that fetch rover.
Note that the little Canadian flag is a primitive weather station on the fetch rover. Anyway, these are the sorts of things that people do to build up a capability that eventually ends up with returned samples being brought back to Earth laboratory instruments that are hundreds of times more sensitive than what you can launch on a spacecraft as a planetary payload. The only caveat is that when you bring these samples back to Earth, there's many more Earth contaminants you have to deal with, be able to identify those and avoid getting them on your sample. So if you have a containment facility in which to look at these samples, it's a two-way containment. You don't want to have anything in the material that you brought back get out, and you don't want all the things that are available here on Earth to get in. Meteorites that land in the Sahara Desert, for example, are known to be colonized by Earth microbes within 24 hours of them hitting the desert. It probably takes more time than that to pick up the ones that are in Antarctica. But the Sahara Desert has proven to us that there are Earth microbes that love meteorites. So what's next for the NASA science program? NASA's got a exploration program initiative that focuses largely right now on the moon, but the budgets that we've been requesting also fund the robotic exploration of Mars. International partners are a key to this strategy, and the ability to have something jointly, for example, with Canada and the new Mars Ice Mapper mission, provided data for potential landing sites. Where would you want to take people if you were going to get there? And the Mars sample return, of course, has the ability to tell us more about Mars per se, but also about threats to human health and safety. Anything else you'd like to put on this one, Vicky?
No, that's fine.
Okay. So this is something that we learned from the Obama administration. We call this the squid chart, but it's still applicable. Technology, exploration, and science. Now, science, exploration without science we call tourism, but tourism isn't all bad these days. On the other hand, science really needs to lean on exploration capabilities if we're ever going to be able to look at places like Phobos and Deimos, and from there or on the surface directly, the surface of Mars, to find out about these compelling questions about life on Mars. Now, you have to ask, why is it you're going to go to Mars? And of course, if we want the way of the Apollo landings 50 years ago, geopolitical reflection was part of that. Who's better? Scientific exploration is a major driver. Robots and their Earth microbes are of interest. Humans and their many more Earth microbes are something we have to be very careful about, because they may not be as helpful in finding extinct life on another planet as all that. But you can land on the planet, or you can teleoperate things from the moons of Mars, Phobos and Deimos. Real estate may be another motivation, just the dirt and the water. Is there anything worth exporting on Mars? So far, we don't know of anything. But if you need water, Mars is a great place to go because we know there's water ice all in lots of places on the surface and certainly on the polar caps. A forward basing for asteroid mining might be something that you deal with at least early in the stage of asteroid mining when you're trying to figure out everything that goes on. A library is something that people have actually pinned on their hopes for Mars. A second place for humanity's capabilities to be plunked down in case we ever need a little bit of help from our friends on Mars. They'll have a library that tells them exactly how to do what we need to do here on Earth. And then, of course, tourism, again, is one of those great things. But right off the bat, you're probably not going to play hockey on the icy parts of Mars because they're mostly covered by dust. So part of the future of Mars exploration and life on Mars has to do with whether or not you can get the kind of people that go and look at Glacier Bay, Alaska, to want to go ahead and look at icy parts of Mars. And whether they can do that safely, whether they can do that as something you'd like to do with your last bit of mortgage payment. These are the sorts of things that you need to make it happen. A launch vehicle, a near-Earth crew vehicle, a Mars transfer vehicle that protects you from radiation and gives you some ability to have countermeasures against microgravity. Solar electric cargo tug that you would want to get there earlier than you and land your nice space habitat. You want to have pressurized rovers so you can get around in style, and a Mars ascent vehicle. So yes, you want to go home. Of course, all of the landing on the surface of Mars with humans only makes sense if there's a surface EVA capability, extravehicular activity that somebody can wear. Because the smallest space suit that we have right now masses 140 kilograms, which isn't so bad if you're standing on something that only is going to take up a third of that. On the other hand, if you want to start and stop, you've still got to deal with momentum. So the propellant for Mars ascent vehicles are something we think we can get from the environment of Mars, whether it's ice itself or whether it's from the atmosphere.
Yeah, so this is where the MOXIE experiment is leading to. It's trying to get oxygen out of the air as a fuel and a propellant.
But a completely different way than hydroponics do it. So MOXIE will split carbon dioxide, and your typical green growing plants split water. And that makes hydrogen available for them to add to carbon dioxide and make sugar and all sorts of other intriguing salad vegetables. But how you're going to be able to get around on Mars depends a whole lot on the approach you take. And therefore, you have to look at where people should go. You want access to water, oxygen, you want protection from radiation, which thankfully is provided by that big planet that you're sitting on, at least half of it, and then fuel for vehicles. So you're going to be looking at a lesser quality of something that you want to burn in a vehicle. But of course, you want to make sure that there's enough aviators breathing oxygen that you can step outside. Vicky? These are just really cool shots that Vicky has provided showing you where the water is on Mars.
Right, and so the middle shot there is some of these new data that are coming back from Mars radar that are suggesting that there might be layers that are ice or water rich under the surface. So that's emerging data. So we know that there's ice. John had referred to the ice caps. So I think just the North Polar Cap alone has about 100 times as much fresh water as all the Great Lakes in North America. So Mars' ability to hold on to water in the form of ice is pretty good. There's quite a lot of water there. So it does make it the most interesting place for humans to explore after the moon in terms of its proximity.
So this is a map that was put together in a publication that I dealt with about where we're likely to be able to land. If you go up too close to the poles, it's very difficult to use photovoltaic power. You won't get money back from Opalco if you're up there. If you're closer to the equator, yeah, you're in great shape. Good place to have photovoltaics. But the water ice becomes more and more difficult to find. One of the nicest places on Mars to go to look for unusual things with water and potentially for life is the big purple spot to the lower right called Hellas Basin. And that's way down deep compared to most of the places on Mars. And they actually have an atmosphere that may be even as little as a tenth of that of the Earth. Next slide. Unfortunately, long-term duration space flights bring with them all of our commensal organisms, all the things that we live with every day on Earth. And they're not necessarily things you want to have around you. On the left is a picture of a part of the International Space Station where people dry their exercise clothing. That black stuff there is your old friend fungi, different mildew of different kinds, as imaged on the right, show you that things like, even like Staphylococcus aureus, are alive and well inside the International Space Station. And imagine taking that International Space Station to Mars and back, a trip of over 500 days, and you're going to have to get used to your microbes. But you don't want to bring them to your base on the surface of Mars. And as this wonderful Canadian astronaut is showing us, you can do horticulture, but don't bring up plant diseases if you want to go ahead and stock your spacecraft for the ride home. Next slide. And of course, Elon Musk is one of those proponents of these activities, and for a variety of really interesting reasons. But you know, looking at the overlap of who wants to go and who can afford to go is one thing, but the cost of the trip to Mars is coming down. It's the median cost of a house in the United States by Elon's calculations. That may be a little optimistic, but it's certainly something that he can provide in the future better than he provided the ride in the Tesla before. So if you're going to go to Mars in the future, you're going to have to go inside or put the convertible top up, and don't panic.
Yeah, so this is a real image. Elon Musk, to test his heavy launch vehicle, put into, as its payload, a Tesla with a dummy spaceman. And this was rather unknown to the world before it was launched, but there is now a Tesla floating through space that was serving as his test mission.
It gets great mileage. Anyway, but if you were going to go in the real system, you would go in something that looked like this. 17-meter diameter spacecraft. Think about it from a sailboat perspective, which is most sailboats are probably only about 3-4 meters wide. You're going to be in a really interesting situation where you have to manage all of the things associated with keeping people alive in space, but you also have to manage expectations for when they get to Mars, the problems of microgravity deconditioning, and other effects that you might have in a radiation storm, for example. There's got to be a place to hide. All that's being taken into account by SpaceX, and what it looks like in the long run remains to be seen. Tanking in Earth orbit is the idea. Go to Mars, go ahead and use the Martian ice to refill your ship, and then take the ship back to the Earth. And the question from a planetary protection standpoint is that if tourists go to Mars and get sick on the way home, are they going to have a reliable and reasonable quarantine capability to greet them when they come here? A little bit like Ellis Island of the Martian colony. Anyway, I think that Elon has got some great ideas, and basically his idea about the future is that he wants to wake up in the morning and think the future is going to be great. And that's what spacefaring civilization is all about. Believing in the future and thinking that the future will be better than the past. You can't think of anything more exciting than going out there and being among the stars. And it's a great ambition, and it's brought us the lowest cost, most reliable launch system ever. And in the future, there may be one that actually has the name Mars on it. So we'd like to thank you, Vicky.
Yeah, so yeah, thanks to all of the slides and images that we have borrowed from the different space agencies here. And thanks to you all for bearing with us for this interesting Zoom encounter. It's certainly an interesting challenge working from home, and our poor little daughter really wanted to be part of this. She wasn't quite asleep.
That's right. So there are various and sundry visions of the future. This is Robert McCall, University of Arizona Art Museum. And we'd be happy to answer your questions about the past, present, or the future.
Yeah, space itself, I mean, we have Carl Sagan, who very famously made sure that there was a picture of Earth taken from the Voyager missions. And having that far distant picture of Mars, of Earth, not as tiny as the photograph from Mars, I mean, that really has been motivational for the environmental movement on Earth as well. I mean, understanding our planet is so tiny and fragile looking has been motivational to me too.
Carl was very direct about any job with a space agency required bureaucratic courage. And he adjured me to practice bureaucratic courage all the days of my public service. All right, thank you.
Well, thank you guys. I really appreciate it. And I'm kind of keeping, I don't see anything in the chat, but if you have questions, just wave at me, or you can, as I said, if you go to your little icon and you can actually do the hand thing and raise your hand for a question. So. And you must have answered all the questions already.
Well, we have one
Stefan
raised hands.
Mm-hmm. Okay.
And we also shop locally.
Can you hear me?
Yes, Stefan.
Yes, we can.
Okay, hi, yeah. My name is Stefan Michalowski. I live on the island. I'm a retired elementary particle physicist and international civil servant. And I'm retired, so I've been interested in the space program, since I was a teenager, followed very closely. But I disagree entirely with the idea that there's a future for manned space exploration. I don't think there is, but I'm not going to make a speech about that. But I have a question. It seems to me that if the robotic missions, which are wonderful, don't find evidence for life on Mars, or even find evidence there can't be life on Mars, or hasn't been, then I can't imagine any reason to send people there. I mean, I don't know what they would do there. I just can't think of a reason to go and just explore Mars. But if life is found, I think that changes the equation completely, because it becomes a very interesting scientific problem and challenge. But if you send people now to do the experiments much better than robots can, then don't you essentially guarantee that you will contaminate the planet? If people are exploring Mars, which is a hostile, difficult environment, it's almost inevitable that someone will die there in tragic circumstances. There will be an explosion or a fall or a rupture. Some spacesuit will be ruptured in some way, and the entire contents of a human body will be spilled into an environment where you have life, and which can interact with now the Earth terrestrial life. So isn't this sort of a contradiction that really precludes sending people there? Thank you.
Well, Stefan, it's very interesting to hear the question. And certainly, those are issues that have been brought forward many times in my career and before my career. And I think you have to kind of parse it out in different places. First of all, there's this place called Seward's Icebox, where when the US bought it back in the 1800s, nobody thought it was worth anything for anybody. But even if you didn't have ample fish, you didn't have ample oil, you didn't have ample timber, et cetera, in a place called Alaska, there's still lots of people who like to go there for other reasons, none of which are productive economically for you and me, but for people in Alaska, pretty effective. And as a result, the tourist industry there doesn't need to ask whether or not there's a government program to send them there. They just go. And this is much more the kind of a style that some of the space companies have these days, is that they're not looking to be sent as if it were a choice between either humans or robots. They want to go because they want to go. They'd far rather go to Paris than to send a robot there to look at it for them. Now, at some level, of course, if you go back to the science, doing this without understanding what you're doing to the planet is irresponsible. And there is a potential, however, that the economic balance could really be helpful to the scientist who wants to know more about life on Mars and would never get a chance to go there, even with a robot, to the right places, the right times, the right frequency of measurements, without the kind of income that you could bring from human missions that were there for tourism or some other purpose. I'm pretty sure that Mars can be contaminated by human organisms, but I don't think it's going to happen all at once. I spent a good part of my career trying to make sure that the robotic spacecraft we sent to Mars were clean enough so that they weren't going to spread contamination or have their actual programs of research affected by contamination. But you know, I do think that once we start sending something like humans up there, the ability of humans to contribute at all to the study of life on Mars is got to be dependent on whether or not the humans' contamination is understood and their interaction with Martian materials is understood. Because nobody wants to discover life on Mars for the first time when it's in their lungs. So I think there are a number of interesting questions. I'd love to discuss them with you more so. But there are definitely people who, whether we think it's worthwhile or not, will try to make money sending people to Mars.
Thank you, Stefan. Are there other questions at all?
Hannah has one. Is it my bedtime yet?
Looks like there's a couple in the chat.
Okay. So we've got, first of all, will you post the recording on the library website? Yes, we will. From Dick Coffey, any comment on Gilbert Levin's conjecture that Viking found signs of life on Mars in the 1970s?
So that's really interesting because Gil is a longtime friend of mine, and Gil had the labeled release experiment, which provided, excuse me, Hannah. He had the labeled release experiment that he did with Patricia Streit, and basically all of their pre-flight requirements for detecting life were met. But at the time, the labeled release experiment was countered by the fact that the mass spectrometer, GC mass spec, did not find any organic molecules. Well, since that time, we've actually found quite a few organic molecules at the site of the Gale crater. And so the concerns about the labeled release experiment were never actually addressed with this new understanding of Mars organics in mind. And I would love to have seen Gil stay active in the community and actually be proposing to fly that instrument again right now in conjunction with a place where they might find even more organics than they found in Gale Crater. And I'm hoping that if he doesn't pick this up himself, because he's older than I am, that he will get some help from some younger students who can go ahead and sit through. Because I think if I were to go to a court of law and say that there's nothing to worry about on Mars, I would point to the labeled release experiment that Gil did, and I'd point to these organics from the Curiosity mission to Gale Crater and say, all of the data we have are consistent with life. We just don't see it ourselves.
Great. Thank you. So Nancy has a question. What is the time required to travel to Mars? And is it the same amount of time to travel back to Earth?
Well, the trick about getting to Mars is that you have to lead it. So when Mars is quite a ways behind us in the orbit around the sun, that's when we start out. We send a spacecraft going across a minimum energy trajectory to actually be run down by Mars effectively at a very high rate of speed. So 12,000 miles per hour is how hard you would get hit by Mars if Mars didn't have an atmosphere. But Mars does have an atmosphere. So you can do that, and it takes on the order of 7 months for that to happen for most typical trajectories. There are hopes that we can go ahead and add more propulsive characteristics to that, because that's all a coast. But if you want to propel yourself across that gap, you can get it down to 3 to 5 months. But we don't have rocket engines that can do that right now at a cost of propellant that makes that possible, but we're working on them. On the way home, it depends on exactly the route you take. But again, it's about 7 months getting back. And the difficulty is you can't leave right away. So if you go land on Mars, you go through your 7 minutes of terror and you land on the surface, you need to wait either 30 days and go right back, or you wait a total of 500 days before you get back to Earth. So you only have a few things to do. There are different kinds of missions that can actually get you to opposition. And so you would actually land on Mars on the other side of the solar system, as opposed to in direct contact with Earth. Those are all interesting, but they've never been used for successful spacecraft.
Well, I have a question. In terms of the two moons, Phobos and Deimos, do you think that the study of them will reveal things about Mars itself?
It conceivably could, but the basic thinking about Phobos and Deimos is that while they could be have a few different kinds of samples from Mars on them, that most likely what you're going to find out is that both Phobos and Deimos are captured asteroids. And they have all the orbital characteristics that lead people to be suspicious about that. We've recently, the Space Studies Board of the National Academies of Science, Engineering and Medicine, have done a story board kind of a thing where they looked at what's the potential for a mission to Phobos or Deimos to bring back a sample of Mars as something that we would like to control. And it was very low probability that they would ever encounter something from Mars, and a lower probability that they would gather it up and bring it back. But it's interesting because there is this, what we call rock-aided panspermia that goes on. If you hit the Earth or Mars with a large impact event, there are a certain number of those materials that are knocked off of the, say, Mars, that go into orbit around the sun rather than around Mars itself. And those orbits then cross the Earth's orbit over a period of time. So we get a natural interchange of materials between Mars and Earth every year. And it's estimated that roughly on the order of 40 kilograms of Mars comes to the Earth every year. Most of it lands in the ocean, and much of it that's known lands in places like Antarctica or in the Sahara Desert. Now, what's funny about that, of course, is that, you know, back in the days of the Earth's early life, Mars and the Earth were pretty much twins. And there's no guarantee that life started here on Earth itself before it started on Mars. And so actually large impact events on the surface of Mars, if Mars had life, could have knocked that life into the solar system, the inner solar system, to land on Earth. So in one sense, we may all be Martians if we're descended from organisms that were brought to Earth from Mars 4.5 billion years ago, 4 billion years ago. You never know.
Thank you. Are there any more questions? I'm not seeing any. So John and Vicky, thank you so much for doing this. It's just fascinating, and it's really great to get to know you virtually, and I hope we get to know you actually in person sometime. And thank you very much for sharing all this incredibly detailed knowledge of Mars.
It was a pleasure. I hope it wasn't too detailed, but we can answer simple questions too, like, you know, what do you eat when you go to Mars?
And as I said, we will be putting the recording, give us a few days, but we will be putting it up on the library website. And I know some of those diagrams were very detailed, and we'll probably all want to go back and take a closer look at them. So,
Really. Thank you, Boyd.
yeah, thank you very much. I really appreciate
Thank you all for whoever attended.
Yeah, thanks.
it. Okay.